hopefully give you food for thought. But if it's like super fascinating and interesting, then you're warmly invited to stay along for the second half when we're going to get the really exciting stuff. Then we're beyond like the introductory regular seminar. During the second hour, I think Daniela will open up the hood a bit and spill her own deepest secrets about this work and how it works, and maybe talk a bit about future challenges or whatnot. So this is to say that there will be like a first hour regular talk and then a second hour more technical in-depth continuation to also maybe inspire us regarding topics to talk about during the semesters. So without further ado, Daniela, the floor is yours.
So thank you, Jakob, and thank you for having me here. Yeah, as you said, today I'm going to talk about combining SAT and computer algebra for circuit verification. But let me start my talk with the following question, namely, what is 4,195,835 divided by 3,145,727? I mean, obviously, I can't solve this in my head, and I'm too lazy to do that on paper. So let's use a calculator to solve this equation. And type in the first number divided by the second number, and then we get the result. Obviously, we could also use something like Excel for that, or also a computer algebra system if you prefer that. But nevertheless, we see that in each of these tools, we get the same result, namely that the solution is 1.3338. So far, so good. And now I want to take you back in time. So now let's travel back a little more than 26 years ago to the 4th of October, 1994. And on this day, so the reason why I chose this day is because on this day, Thomas Nicely is going to contact Intel about something strange that he observed while doing calculations, more precisely divisions on his computer. And I want to show you now what he observed. So hold on tight and let's go back in time. So there we are now in 1994. And obviously it's kind of a strange version because apparently we already have Windows 95 and we can use a flat screen with an HDMI input, but never mind. And now let's do our calculation here. So I hope this video shows for you. Let's open here our calculator and then do the exact same calculation as I just did with you on my regular laptop. And what we see here right now is that the solution is actually different. So instead of the 1.3338, which we got previously, we now get a different result, namely 1.3337. And that's exactly what Thomas observed, that sometimes he got incorrect results for division. And after making sure that it was not a fault on his side, and it was also not a software bug, but indeed it was a hardware error, he reported this issue to Intel, and this specific error became well known as the Pentium bug, which affected early Intel processors. So in the YouTube video I just showed you, the computer uses such an processor of type SX923, and when we open, for example, CPU word, then we see here on the notes that this processor has indeed the well-known FDiv bug. And so this bug affected the floating point unit in the early Intel processors and had the effect that as we just saw, that this processor might return incorrect results for division. And back then, this led to costs of about $500 million for Intel. And when we think of how much computers and processors are used nowadays, I'm pretty sure that if such a bug would happen today, this would mean serious troubles for hardware companies. So these companies really want to make sure that their hardware is correct. However, even today, like more than 25 years later, verification of arithmetic circuit is still considered to be hard in practice and requires a lot of manual effort to do so. And especially among the arithmetic circuits, proving the correctness of gate-level integer multiplier circuits is considered to be a challenge. And that's exactly what we will consider now in this talk, namely the verification of such gate-level integer multiplier circuits. So we all know how to multiply on paper. And here we have, for example, the binary encoding of 3 times 3. And we now want to calculate the product. So in the beginning, we build the partial product, which is rather easy here because it's all ones. And then we start with the last column and sum up the partial products. So the last column is only one entry. So we have a 1 without the carry. Then we sum up 2 ones, which gives us output 0 and a carry of 1. Then we again sum up 2 ones with output 0 and a carry of 1. So we now calculated that 3 times 3 is equal to 9. Yes. And in computers, this multiplication is executed using these gate-level circuits. So here on the right, you see a 2-bit multiplier. This circuit, so an arithmetic circuit, consists of a set of logical gates. These are these guys here that are connected by wires. And an arithmetic circuit receives then here the binary inputs on top. And according to the gates, the input signals are then processed through the circuit until we receive here the output at the bottom. So this circuit has 2 kinds of gates, namely an AND gate and an XOR gate. The AND gate models logical conjunction, where the output is 1 if and only if both inputs are 1. And for the XOR gate, it's the case that the output of an XOR gate is 1 if and only if both inputs are different from each other. And then let's see what this circuit here computes. So we start here with the first AND gate. It receives 2 ones as input. We take a look at the truth table and we see the output has to be 1. Similar for all the other AND gates in the first row. Then we have now here an XOR gate, which reads 2 ones. So we take again a look at the truth table. We see 2 ones gives us the output 0. Then we continue here with the AND gate, again with 2 ones. So the output is also 1. And then again, we have an XOR gate with 2 ones, and finally also an AND gate with 2 ones. So we see here that also this multiplier computed at 3 times 3 is equal to the output 9. So we can now ask the question, is the circuit correct? And let us compare now the circuit, what the circuit computed to what we compared on the paper. Since it's both time the same output, we can actually kind of conclude, so yes, the circuit seems correct to us because we now tested it and it looks pretty good. Another question is the circuit really correct? And with really correct, I mean that when you have given a gate level multiplier for a fixed input bit width, the question is whether for all possible combinations of the inputs, is the output bit vector always equal to the product of the input bit vectors? So in the following, we will always denote the 2 input bit vectors with A and B. The output will be labeled with S, and then we have the internal gates that are labeled with a G. And yeah, we now want to derive whether, no matter what I plug in here at the top, the output down here is always the product of the input. So how can we do that? I mean, the first idea would now be simply, okay, let's test all possible combinations. But already here for these 2-bit multipliers, we already need 16 test cases. So here on the left, you see all these possible combinations. And I guess you can imagine that this scales pretty bad if we increase the bit width. So as you see here, so for example, if the input bit width is 64, we are talking already about this really huge number. So there's no way that we can test all possible combinations in a reasonable amount of time. And this is now where formal verification comes into the game, because we now want to translate the system and the specification in a mathematical model and then let an automated decision process decide on the correctness of the circuit. And in the past, several formal verification techniques have been used for arithmetic circuit verification. So for example, SAT solving and a large set of multiplier benchmarks were sent to the SAT competition in the year 2016. However, the results showed that actually SAT solvers perform pretty bad on checking the equivalence of multipliers. And this somehow led to the conjecture that SAT solvers need an exponential runtime on these benchmarks. Another technique is based on decision diagrams, so more precisely on binary moment diagrams. And this was actually the first technique which was able to detect the Pentium bug. But here the problem is that it cannot be applied fully automatically because you need to build the decision diagrams in a certain order to guarantee that the size of the decision diagrams does not explode. So you need to manually sort the way how the decision diagram is built. Another possibility would be the use of theorem proving, and that is actually what is used in industries. But also here the problem is that it requires a lot of manual effort. Last year there has been made some progress in this theorem solver ACL2. However, there you need to have some structural knowledge of the multiplier. So also here you cannot directly plug in multipliers purely on the gate level. The currently most successful verification approach for this gate level multipliers is actually based on computer algebra. And it started with these 2 papers, which came out in 2015 and 2016. And in the algebraic approach, we use a polynomial encoding to model the circuit. And this approach now also works fully automatically for non-trivial multiplier designs. Yeah, so the basic idea of the algebraic approach is that we translate the multiplier into a set of polynomials. Then we also have the specification as a polynomial, and we want to show whether the specification polynomial is implied by the polynomials that are induced by the circuit, which actually means that we want to show that the specification polynomial has the same roots than the circuit polynomials, and this algebraically means that what we want to solve is actually the ideal membership problem for the specification. And now I want to go into the details of each of these parts of the algebraic approach. And I want to start now with the specification. So yeah, here you see the specification polynomial when we model multiplication of unsigned integers. And it's actually encoding that the output bit vector, so written down here as a weighted sum, is equal to the product of the input bit vectors. And together with the specification, because we are talking over polynomials, we also need to fix the polynomial ring. And we choose the polynomial ring here over the integers because we are actually, so we want to model integer multiplication, so this seems to be the natural choice. So a comment here, so although each of the variables represents a Boolean variable, the word level specification is defined over the integers. If we want to model signed integers, then the specification is actually the same, but we need to take into account that the most significant bit represents the sign. So that's why we have here now a negative weight. Yeah. In the following, because now our left side is always equal to 0, I remove now this equal to 0. So from now on, I will only represent polynomials like this without writing this equal to 0 on the left or right side. Yeah, and Mina just argued why we choose here the polynomial ring over the integers, but actually we make it easier for us because the integers, polynomial ring over the integers is a subset of the polynomial ring over the over the rationals. And thus we choose now the polynomial ring over the rationals because the rationals are a field, the integers are not, and we want to work in a polynomial ring over a field because this makes things easier for us, and I will explain later in the talk why this is important for us. So we now have our specification polynomial, we have our polynomial domain. So we can now move on to the second part, namely how do we get actually from the multiplier circuits to the set, or to its polynomial encoding. And there we again take a look at the truth tables of the gates, and we encode now each gate by a corresponding polynomial. So for example, here for this AND gate, we get with inputs f and g and output y, we get the polynomial minus y plus f times g. And if we plug in here now the possible combinations, we see that y is 1 if and only if f and g are 1, otherwise y is 0 if either f or g is 0. Yeah, and in a similar style, we find the polynomial encoding of the XOR gate. So it looks a little bit more complex than the one for the AND gate, but it's actually found in a similar way. And because we are working in a polynomial ring over the rationals, we have here now this minus, this monomial now with coefficient -2. Yeah, and then we traverse through the circuit, and for each gate in the circuit, we write down the corresponding polynomial equation, and we start here by the outputs. And here we have the AND gate with inputs G1 and G4, and since it's an AND gate, we get here this polynomial equation. And then we move through the circuit and do this for every gate in the circuit. And we sort the polynomials, or especially the terms, in a specific way. Namely, since we started here at the outputs and traversed up to the inputs, we can sort the polynomials in such a way that always the output variable is larger than the input variables of a gate, And by that, we get this shape that always the first term in the polynomial, so the leading term, consists only of the output variable of the gate. And this property will also be important later on. Yeah, and after we've defined all the gate polynomials, we need to take now we need to model that the input is of the Boolean domain. And we do this by adding so-called Boolean value constraints, which simply encode that so this equation is equal to 0 if and only if a1 is either 0 or a1 is 1. So here we model that these variables can only take the values 0 or 1. And so these are not in the Boolean value constraints in an expanded form. Yeah, and so we have now this encoding, but actually we can find many more such relations in the gate, in the circuit. So not only do we have here this our gate constraints and the Boolean value constraints for the inputs, but in fact it also holds that the internal variables are all of the Boolean domain, or we can find other constraints which always are equal to 0, namely, for example, here this XOR AND constraints, which says that the output of an AND gate and an XOR gate, which both receive the same inputs, can never be both 1 at the same time. And we call all these circuit relations the polynomial circuit constraints, and they have the following definition. So a polynomial is such a circuit constraint if for all possible inputs, so for all combinations of the Boolean variables on the inputs and the resulting values that are computed by the circuit for the G1 to Gk and the outputs, the substitution of these values in the polynomials always gives the value 0. And we collect now all these polynomial circuit constraints in a set which we denote here by I of C. So this set contains then all the relations that hold in the circuit C. And mathematically, this set now generates or is an ideal. An ideal is a set of polynomials that is closed under addition. So whenever we take two elements from an ideal, their sum is also contained in the ideal. And it's closed under multiplication by any polynomial from the polynomial ring. So when we take a polynomial from the ideal, we can multiply it by any other polynomial from the ring, then the product also is contained in the ideal. So that's the definition of an ideal. And we are now particularly interested in one such circuit relation, namely in the relation between the outputs and the inputs of the circuit. So we say that a circuit is called a multiplier if the specification, which is the relation between the outputs and the inputs, is now contained in the ideal. And you see, this brings us now down here, what we want to solve is, in fact, the ideal membership problem. So we want to show whether the specification is contained in the ideal that contains all the circuit relations. Yeah, and for that, we actually need one other definition, namely the basis of an ideal. So a set of polynomials is called the basis of an ideal if all polynomials that are all elements from an ideal can be represented as a linear combination of the basis elements. And if that's the case, then we also say that the ideal I is generated by this given set of polynomials G. And when we have given an arbitrary basis G of the ideal, it is not obvious how to decide the ideal membership problem. What we in fact need is a basis with certain structural properties, and these bases are called Grübner bases. So the exact definition of the Grübner basis is not important to us, but what is important is that it offers a decision procedure for the ideal membership problem in a polynomial ring over a field. And that's why it was so important for us that we choose the rationals and not the integers in the beginning, because now we can use the theory of Grübner bases to answer the ideal membership problem. Then it holds that every ideal has a finite Grübner basis, and when we have given an arbitrary basis of an ideal, then we are able to compute the Grübner basis. And so this sounds now pretty good for us. So we now know how to solve the ideal membership problem, but there comes the big but. So computing a Grübner basis over the rationals and deciding the ideal membership is actually known to be in X-space complete. So it's pretty expensive to do it that way. However, since we choose such a specific ordering of the polynomials, we can actually use a shortcut for the Grübner basis computation. But first we need to deal with a second problem. So I told you that from an arbitrary basis, we can compute a Grübner basis. But the fact is, for our ideal I of C, we do not know any basis. So we only know that it's the big set which contains all the circuit relations. However, we can deduce some elements of the I of C, because we always know that the gate polynomials and the Boolean value constraints are contained in this ideal. So let us now generate a second ideal, which we call J of C, and this is not ideal that is really generated only by the gate polynomials and the Boolean value constraints. And because we now choose this specific term ordering, namely that the output variable of a gate is always greater than the input variables, the following can be shown for J of C, namely that in fact the gate polynomials and the Boolean value constraints are already a Grübner basis for the second ideal. So this means we do not have to compute the Grübner basis, but in fact by choosing this term ordering, we have already written down a Grübner basis. And the proof idea behind this is that we repeatedly apply Buchberger's product criterion, which allows us to skip parts in the computation of the Grübner basis. So in fact, in our case, we do not have to do any computation. So now we have our two ideals. So we have now the ideal I of C, for which we want to derive the ideal membership. And we have now our second ideal J of C, for which we already have a Grübner basis. And we can actually show the following. So for all acyclic circuits, we have in fact that those two ideals are the same, which boils down to soundness and completeness of the method. Yeah, and since we now have a Grübner basis for our ideal I of C, we can apply the following verification algorithm, namely that we reduce the specification by the gate constraints and Boolean value constraints until no further reduction is possible. then the circuit is a multiplier if and only if the remainder is 0. So for the reduction, we use some kind of polynomial division. And I now want to show this to you on our small 2-bit multiplier. So here on the left, we have all the gate constraints and the Boolean value constraints. And here on the right, we have the specification. And yeah, so let's now reduce the specification here by the first polynomial. So by this minus S3 plus G1, G4. And since we have this special shape of the polynomials, where all the leading terms consist only of one variable and the leading coefficient is -1, in our setting, the polynomial division actually boils down to replacing here always the variable of the leading term, so in this case the S3, by the complete tail of the polynomial. So in this case now, instead of S3, we get now G1 times G4. And in the second step, we do this now for this S2 and replace the S2 now here by the complete term tail of this polynomial. And what you see here too is now that in the second step, we introduced here this monomial 8 times G1 times G4, which now in the second step cancels again. So it sometimes, or actually it quite frequently happens that we introduce monomials during the reduction, which then will get cancelled in later steps. And these monomials, which we introduce in during some reduction, and they only get cancelled later, they are actually a big problem for us in the verification step, because sometimes we, not sometimes, we get quite a lot of them, and this slows down the verification step significantly. And I will show you a graphic for that in a second. But now let's continue here our verification steps. So in the next step, we reduce here by the G4 and get the G2, G3, and so on and so forth. And we continue until we now got our final remainder 0. So here we now see that the multiplier I showed you in the beginning is indeed a correct 2-bit multiplier. What happens now if we introduce an error? So let us take here, for example, the input of this gate G3, which goes here to the A1, and move it to read the A0 instead. So then we also get here now a different gate constraint. And in the verification steps now the following happens. So the beginning is the same until we are now here at this step, where we introduce now the error. And then we are left at the end with a remainder which is unequal to 0. So at this point, we do not have any polynomial left on the left side, which can be used to reduce here this final remainder. So we know now that the circuit is incorrect. And from this remainder, we can also derive counterexamples, so concrete assignments for the inputs where we see that the circuit computes a wrong result. So for doing that, we choose an assignment of the inputs in such that this polynomial evaluates to something which is unequal to 0. And so let's, for example, set A0 and B0 both to 1 and A1 and B1 both to 0. then we get the effect that the first monomial evaluates to 0 and the second evaluates to 1. So we get 2, which is unequal to 0. For this assignment, we actually would expect the circuit to compute that 1 times 1 is equal to 1. But when we plug the input in here and then compute the signals, then we actually see that in that case, the circuit computes 1 times 1 is equal to 3. So we have now here one specific counterexample for which we see that the circuit is indeed not correct. Yeah, so as I already hinted with these green boxes during the verification algorithm, is that if we would apply this algorithm just as it is like that we reduce the specification by the elements of the gate, also by the gate constraints and the Boolean value constraints, then this has the effect that for larger multipliers, the number of the monomials in the intermediate reduction results increases drastically. And for our setting, this had the effect that we could not even verify an 8-bit multiplier within 20 minutes. And in related work, they actually did some experiments on the monomial size after each substitution steps. And so they choose a simple multiplier architecture. This is always here, the blue line, and some non-trivial multiplier architecture. This is here, the red line. And we see, so they did this for 4-bit, 8-bit, and 16-bit multipliers. And we see for the simple multipliers, kind of the monomial size stays quite constant before it reduces to 0 finally. But for non-trivial multipliers, we see here this big up and downs, especially a big up in the beginning, before it then drops to something constant and then reducing to 0. And here for 16-bit, they reached over more than 10 million monomials in such, also in one of the intermediate results of the reduction, and also that it timed out for them. So that's why we cannot use this reduction algorithm like out of the box. And that's where we and also the other groups are now working on to find ways to overcome this issue of the large increase of the monomials. And I now want to show you my approach to overcome this issue. So the first idea which we are using is that instead of taking the complete specification and doing this reduction steps, we instead do an incremental verification algorithm where we cut the multiplier into slices and then verify, incrementally verify the correctness of each slice. And the idea is basically taken from how we do the multiplication on paper, because also there we first build the partial product and then we do this column-wise summing up. So where we take the partial products of each slice, add it to the incoming carries, then write down a sum bit and send carries to the next slice. And that's exactly how this algorithm works. So we cut here the multiplier in such a way that each slice contains only one output bit. And then we start at the most significant output bit and verify the correctness of these slice until we are here at the least significant output bit, and there we check whether the final remainder is 0. Yeah, so our input format is actually not this gate level circuit as you see here on the left. Instead, we use AND inverter graphs. Yes, in any inverter graph, each of the nodes represents logical conjunction, and the marking on the input edge represents a negation of the input signal. So this AIG here on the right is the AIG encoding of this 2-bit multipliers, which we used now throughout the talk. So for example, here, this AND gate, which reads B0 and A0 as input and S0 as output, is represented by this node, which gets here input A0, B0, and has output S0 too. Yeah, and for the XOR gates, we need a couple of more of the AND gates. But the reason why we are using it, it's because it's very easy to deal with, and it's actually a standard format for to represent hardware circuits.
So just to double check, Daniela, so an AND inverter graph, that's just what we theoreticians would call a Boolean circuit, but the gates are AND and NOT, is that correct? Kind of, except you put the knots on the wires, I guess. Like
yes, we
dots.
put, so here that the knots are on the wires.
Okay.
What's the difference between the squares and the circles or the ovals?
So could you say again?
These squares correspond to AND gates and ovals correspond to?
No, sorry. So these squares here, like this 2, 4, 6, and 8, they represent the inputs again.
Okay. And the circles are all AND gates.
Exactly. These are all, so the ovals, these are all AND. And the filled dots, they represent the negation. Okay. And the triangles are the labels for the inputs and the outputs. Yeah, so this was now the AIG for the 2-bit multiplier. Let's now increase the size. So here you see an AIG for a 4-bit multiplier. And when we take a closer look, we can identify certain substructures in the AIG. Namely, this orange, so the orange marked ones, they define a full adder. Then we have here a half adder. This is how we present an XOR gate now in an AIG. And then we also have here several nodes which only have one outgoing edge. And what we now want to do in a pre-processing step is, because you see here, for example, in the half adder, the internal nodes, so these two, they are only used internally. So what we now want to do here is we want to eliminate these nodes and represent the output, so this one and this node here, directly in the input of the half adder. And you can also see here the same for the full adder, that we also have here quite a lot of internal nodes that are not connected to anywhere outside this full adder. Only here the sum output bit and here the carry output bit of the full adder are then used in other structures, but the internal ones, they are really only used in this full adder. So that's why we want to eliminate them first before we do the specification reduction, because this helps us to reduce not only the number of reduction steps of the specification, but in fact we also get a simpler representation of the Gröbner basis. And so for variable elimination, we use the elimination theory of Gröbner basis. And in our first attempt, we really identified syntactically the subcircuits in the AIGs and then eliminated the internal variables. So we had our schemes for detecting the full adders, the half adders, the XORs, and then also for eliminating the nodes with the single dependency. But we modified this elimination scheme. So because the reason is, I mean, if you do syntactic pattern matching, then also small changes already in the pattern had the effect that we could not detect the patterns anymore and could not apply the full the rewriting steps anymore. So what we now do instead is we have some kind of repeated elimination of variables with a single dependency. This does now not rely on specific patterns anymore. And in fact, it also subsumes all the others rewriting schemes where we really identify the subcircuits. Yeah, and as I said, for that, we use the elimination theory of Grosvenor bases. So if we want to eliminate a variable in a Grosvenor basis, we first need to fix an elimination order. And for that, we split our variables into two disjoint sets, namely in the one variables we want to keep, which are now written here by Y, and in the ones which we want to eliminate, which now written here as the set. And in an elimination order, we now need to order the terms in such a way that all terms that contain variables which shall be eliminated are larger than all the terms which do not contain these variables. Yeah, and then the elimination ideal is simply defined as the intersection over the polynomials ring with the variables which we want to keep. And the elimination theorem of Grosvenor bases now tells us how we could compute a Grosvenor basis for the elimination ideal, because obviously, again, we want to have a Grosvenor basis for our method to work. And so the elimination theorem says that we need to compute a Grosvenor basis with respect to the elimination order, and then we simply kick out all the polynomials that contain variables which shall be eliminated, and then we have found a Grosvenor basis for the elimination ideal. However, as you remember, I said that computing the Grosvenor basis and then answering the ideal membership is X space complete. So this does not sound too promising. But again, we can here make use of our special shape of the polynomials, namely that all the leading terms consist of only one variable, and all the variables are also different from each other because for each gate we only define one polynomial. So all our leading terms are unique. And let's do the following example. So I've written down here now an ideal with the following ordering. So that's how these polynomials are ordered now, where O is larger than X, larger than Y, and larger than A and B. And let us now assume that from this ideal, we want to eliminate Y, because we noticed that Y is an internal variable for us. So let's get rid of this. And what we do now is that we compute the remainder of the polynomial with leading term O and reduce it by the polynomial with leading term Y. This has the effect that actually all the Y's in this polynomial are replaced by the tail. So in this case, AB. And then we add this polynomial to the Grosvenor basis. And we are always allowed to add polynomials to Grosvenor bases that were derived doing polynomial operations. And then because we have two polynomials with the same leading term, we can eliminate one of the polynomials, because so this is also from the theory of Gröbner basis, that when you have two polynomials with the same leading terms, you're always allowed to kick one out. So obviously we will kick the one, we choose the polynomial which contains the y and remove it from our Gröbner basis. So at this point we are now left with these three polynomials. And let's now see what happens when we now choose the variable ordering such that y is the largest element. Then we see that actually nothing changes, because y only occurs in one polynomial where it is already the leading term, so it cannot move any further in front. And then we do the intersection, so we simply kick it out, and that's how we get the Gröbner basis for the variable elimination. So you see, in fact, of doing this Gröbner basis computation for different variable ordering, actually, in fact, what we do is we replace all occurrences of the variable which we want to eliminate by the corresponding tail of the polynomial, and then delete all the variables, all polynomials that contain the variable which we want to eliminate. Yeah, and all of what I just said can be written down in these two beautiful theorems, but I'm not going into detail of them. So with these two techniques, so the incremental verification algorithm and with doing the variable elimination, so prior to the incremental specification reduction, we could already verify simple multiplier architectures pretty effectively. So in this, actually, you see such a simple multiplier architecture. So this has now an input bit width of 8. And this multiplier uses an array accumulation to add up the partial product. So this is here kind of this block down here, where full adders are arranged now in a kind of grid-like structure to sum up the partial products. And then here on top, we have a ripple carry adder, which contains consists of a sequence of full adders, which are used to compute the final outputs of the circuit. So this multiplier has a very regular structure, but it's not very efficient, because at first we need to wait for the signals to be accumulated. And then we need, especially here, need to wait for the signals to be rippled through the whole adder until we get here our final output signal. So that's why in practice there are different multiplier architectures which are way more efficient. So for example, this one here, where instead of an array accumulator, we use now a Wallace tree accumulator, which reduces now the delay of the accumulation step. And then instead of a ripple carry adder on the output, we now have here a carry look ahead adder on the top. And in the carry look ahead adder, instead of waiting for the carry to be rippled through, now the carries are computed at the same time than all the output bits. The accumulation step is still easy to verify using computer algebra, because again, it consists of the full and half adders that are arranged in a different pattern. But what's really hard to verify is here this carry look ahead adder on top. And for the reason, I first want to zoom in a little bit into the carry look adder, and then let's color some gates. Because what you see here is that here, this single orange node on top is computed using here the sequence of gates, which only have which all of them have only one single output. So there is no cancellation happening. So during reduction, we need to remove all these single nodes to represent here this output bit. And in fact, this sequence represents a sequence of OR gates, and this OR gates is what makes the sequence of the OR gate makes it so hard for computer algebra. And the reason is the polynomial representation of the OR gates. So here I have now a sequence of 3 OR gates, and when we see now that we want to represent here the output of the last OR gate in terms of all the inputs, we need to remove these 2 variables, so the O1 and the O2. And if we do this in the step, we get now a polynomial here with 15 monomials. So already for 3 OR gates, we derive a polynomial with 15 monomials. And in fact, in the example which I showed you before, we already have a sequence of 8 OR gates. So you can see the representation of the sequence of OR gates grows exponentially. So it's really bad for us for the computer algebra approach. However, we noticed.
So just a question. Yeah. So maybe I'm jumping ahead, I guess. But like, am I correct that if you look at this expression that you had on the previous slide, it would have been really nice to have formal variables for negated literals? So then I would have written it something like the output is 1 minus times of the negated inputs.
Yeah, so here it could definitely work that for these OR gates we can if we choose here now variables for the negation, then I think this should be representable with only one monomial. If I'm not
I can do 2. I think I do like one minus the product of the negations, because if they're all false, then we're screwed. But otherwise, we know that everything is true. But then the problem is that this, of course, screws up, like, and you have to throw them into, like, where do they end up in the Grosvenor basis ordering, as Massimo is already noting in the chat. And this is like,
yes.
But if we somehow didn't have to worry about this, Massimo, let's be a bit more visionary.
That would be great.
Yeah. These are and I'm mentioning this because these are the twin variables that theoreticians sometimes throw in when they do these algebraic proof systems.
Yeah, because as you pointed out, so I think that's the danger, because they are like on the same level than the variable, like the negation and the positive variable. And sometimes you want to use them, sometimes you don't, and then you need to tell the Grosvenor basis algorithm really especially where to use them and where to not use them, and please don't throw them away. So Massimo is writing, this is essentially like writing the OR as the negated end of negation. Yes. So the fast answer is yes, but I need to think about it like a little bit more about that. But let me continue here. So what we observed. Because so 2 years ago, in 2019, we noticed that actually checking the equivalence of adder circuits is quite easy for SAT solvers. And this led to the following idea, that namely we identify where there's the border between the accumulation step and the final stage adder. So the last adder in the multiplier, then we make a cut here, and we replace the final stage adder by the simple ripple carry adder, which we can verify using computer algebra. And for the correctness of the adder substitution, we choose SAT-solving to check the equivalence of the two adders. And for the rewritten multiplier, we then use the computer algebra approach. So yeah, so for checking the equivalence of the adders, we take both adders, then generate a bit level multiplier, so translate the whole AIG into the CNF. The CNF is given to the SAT solver, and to show the correctness, the SAT solver then needs to return ansat for us. And as I said, for the rewritten multiplier, we use the computer algebra approach. Yeah, in the beginning of our work, we used existing computer algebra system for doing that, because I mean, they had all the algorithms implemented. So we choose specifically Mathematica and Singular for circuit verification. Yep, these tools have a lot of algorithmic power. For example, Mathematica has more than 5,000 built-in functions, and all these Scrivener basis libraries, they were easy to use. But however, they are designed for general purposes. And I mean, our polynomials, they really have this specific shape. And these computer algebra systems, they could not really make, I mean, we had to add all the special constraints to tell them about the shape of our polynomials. So we then decided to implement our own reduction engine, and there we are already now at version 2, which is going to appear at TechUs in a couple of months. And AMOLED 2 is implemented in C++, contains about 6,000 lines of code, and it automatically applies the adder substitution and the circuit verification. And all the polynomial algorithms which are implemented there are designed to make use of the properties of the polynomial, so that the leading terms are all the single variables and so on. And what we also do is that we apply on-the-fly reduction of the Boolean value constraints. So in fact, we always calculate that x times x is equal to x and not to x squared. Yeah, and here on the right, you see how we typically tool flow for AMOLED. So at first, we give it the input AIG, then the adder substitution happens, where AMOLED outputs the CNF encoding, which we can give to a SAT solver, for example, KeySAT, to tell us whether the replacement of the final stage adder is correct. And the rewritten multiplier is again an AIG, which is then given again to our tool AMOLED, and where then the verification step happens. Yeah, now I want to make a quick demo of AMOLED. So what we choose here now as the input is now a multiplier with input bit with 512, so a rather a large example, and we directly call AMOLED with in the verification mode, because I know that the final stage adder of this particular benchmark is already a simple ripple carry adder, and we add here the -v2 flag so that we see some statistics. Yeah, in the beginning, some statistics are printed. So what we can see here is that this particular instance consists of more than 2 million AIG nodes, and the allocation steps are happening. After that, the pre-processing steps are happening. So we see here how many variables are, for example, were eliminated during from internal XOR gates. So we see that's like more than 500,000 of these nodes were eliminated. And after the pre-processing is finished, we start reducing now as we do now the slice-wise reduction. And we always print now the result after the reduction by one slice is finished. So this is now the intermediate polynomial after reducing by the first slice. And what you see here is that we actually really deal with quite large coefficients in these polynomials, because we really need to encode 2 to the power 1023. Yeah, and when we wait, so the polynomials get larger and larger with the slices, and we can even zoom out a little bit. They will still get larger and now fill the complete display. But when we wait long enough, they will get small again until we reached here now slice 0. So the last slice where it says that the remainder is 0. So the circuit
I think your
is correct.
screen, at least on my side, your screen is not, I still have sliced 1021.
Okay. Huh. Then maybe I quit the sharing and start again. Maybe this helps. Did this help for you?
Yes.
Good.
Things are shrinking a lot, and I can now see slide 0.
Yes, perfect. So then the magic happened for you. That, yeah, the slice 0, so the final remainder is 0, and indeed we get the message that the multiplier is correct. And so verifying these 512 bit multipliers now only took us 43 seconds. So remember in the beginning I told you, like with our initial approach, we could not even verify an 8-bit multiplier within 20 minutes. And now we can verify 512-bit multiplier in 43 seconds. So that's pretty cool. Oops. So yes, but now the question is the circuit really, really correct? So can you trust my implementation, or is even the verification process itself correct? And so what we want to do is now we want to validate the result of the verification process. So we want to generate machine checkable proofs that can then be checked by independent proof checkers in order to increase the trust in the verification result. Yeah, so what we now want to do is we want to monitor the reduction, the steps in the reduction algorithm. And I won't go too much into detail about this proof logging, because this was actually my plan to present like after the break, so where I want to go more into detail about this method. But what we do here during proof logging is that we write down a sequence of multiplication and addition steps which help us to verify or to validate the ideal membership of the specification. And here you can see kind of the history of our proof system. So this was like how we defined it in 2018. And from then on, we worked a little bit on, as we worked on deriving shorter and more concise proofs. So this is a short part of how these proof certificates look now for our examples, or like our benchmarks. Yeah, and for checking these proofs, we implemented proof checkers. So the first one is Spectrum, which worked on our initial proof system. So it supports only the older PEG formats. And our most recent one is here PEG-check, which supports now the new calculus, but it's also backward compatible to the older PEG formats. And as I said, after the break, I will go into more detail about the proof logging. Yeah, but now you can say, I mean, hey, you implemented the verification tool and you implemented the proof checker, so from the same person. So are we really sure that the circuit is not really correct? And there I can also say yes. So because with my co-author, Matthias Fleury, actually this was his work, he implemented the proof checker PASTEC in the theorem prover Isabel, which relied on Isabel's refinement framework. So we start with the abstract specification on the ideals, and in the final step, we then got an executable proof checker. And PASTEC is contained in Isabel's archive of formal proofs and consists of about 8,000 lines of code. And finally, before the break, I now want to show you some experiments. So we are not the only ones working on that. So in essence, 2 other groups are also working on verification of 8-level integer multipliers. So the first ones here are located in University of Massachusetts, and the second group is located at the University of Bremen. And we now want to compare our approaches to their work. So from our side, like the computer algebra system Mathematica, so our first attempt, and then our reduction engine AMULET, and now the most recent one, AMULET 2, compared to an ABC-based tool from the University of Massachusetts and to the tool RefSCA from Bremen. In the first experiment, we consider now 384 different multiplier architectures, so simple and complex ones, all with an input width of 64. And the time limit in this experiment is set to 300 seconds. And here you see a CDF plot on the left. So on the x-axis, we have listed here the CPU time, and on the y-axis, the number of solved instances. And what you see here is actually with the computer algebra system, we were really only able to solve the most simple multiplier architecture out of these benchmarks. And with our reduction engine, AMULET 1, and especially now with AMULET 2, we made now a big jump, and AMULET 2 is actually able to verify the complete benchmark set. And the second experiment I want to show you now, we take the simple multiplier architecture, so the one with the array accumulator and the ripple carry add on top, which I explained earlier, where we have now different input width, so between 128 and 128 and 2048. The time limit in this experiment is set to a day. And here we actually see that also now Mathematica here works up to bit width 512. But with AMULET 2, we are now able to verify also this large benchmark. So here this 2048-bit multiplier within an hour. And this dot here, so this 512, this was exactly the multiplier for which I did the demo earlier. Yeah, and with that, so already brings me to the end of this presentation. So we get now the following conclusions. So we can decide whether circuit is correct, because yes, we have tested some cases. If you want to know whether the circuit is really correct, we apply formal verification for answering, is the circuit really correct? I can say yes, because we generated and checked the proof certificate. And for really correct, I can say yes, because we used a verified proof checker. And with that, I want to conclude the first part.
Thank you, Daniela. So on behalf of all the listeners, I'll do my private applause, which I'm sure people are joining. Questions to Daniela? There are two questions in the Q&A. Can you see it? We should read it.
Yes, I can see it. So the first one by Victor is, if a circuit is incorrect, can the non-zero remainder at the end help to pinpoint where it's gone wrong? So there's also some research done by other groups where they either want to locate the error, and it's not directly possible to say like at which part of the gate or directly which gate is the wrong gate, but what it's possible, because you can see it from the like from the coefficients of the remainder, you can pinpoint the cone of influence from the output bit. So you kind of, what to say, so you can narrow it down to where the error might happen, but as far as I know, there's no result that you can really directly pinpoint where it's gone wrong. I hope this answers your question.
But it helps you to, like, as you did in your example, you generated an error. So like for purposes of debugging, you get looking at these polynomials, you generated an input that was wrong, namely something that actually made this remainder evaluate to not zero was then like something that clearly the circuit got wrong. Is that right?
Yes. And I think the way it's done to pinpoint the errors is like to test actually several cases and then kind of build the intersection and detect which gates are like always deliver the wrong results so that you can see where it's gone wrong.
So then there's another question by Mina. So if the AIG is a formula, that is, if it has the structure of a tree and only inputs are replicated, would the verification be easier? How would that be explained from the algebraic viewpoint in practical terms? Degree, number of monomials. In theory, this would be verifying NC1 as opposed to verifying P. The replication of inputs already seems to make things really hard.
I have to say I don't really have an answer to that right now.
I guess one stupid answer is I wonder if it would ever be a tree, right? If it somehow, my feeling would be that you always get some kind of evil looking DAG. If it's an interesting computation. But I don't know. Armin, Paul, any comments?
Yeah, sure. So as Karam is pointing out, so the AIG is a DAG. That's true.
Yeah, but DAGs could still be tree-like. I think that was Mina is asking about. Like we could be lucky so that somehow that every partial result computed by the AIG circuit is used for only one input.
Yeah, and then I mean, as Armin points out, you can turn the AIG into a tree by kind of extended resolution. But then the question, I mean, I guess then you would add quite a lot of overhead to build it into a tree. And I don't think that it makes the verification. Yes, I guess then the verification would be hard because, I mean, what we rely on in this verification step is on this cancellation of of monomials with equal, so which share the variables, and then when you add further variables, then I don't think that this cancellation immediately happens, and then I guess that the verification remains too hard because the polynomials grow too much. That's kind of my intuition about that.
So since I'm not sure if the chat is visible for people looking at the recording of this, I'm reading out that Paul is commenting that converting every output into a separate tree would blow up to a large tree. An array multiplier would become exponential size.
Yes. So, and this actually also relates to Massimo's question in the chat, because the natural approach would be to use the polynomials over the field F2, because obviously this would reduce the coefficients and would reduce the degree of the gates. But the issue is that we need to write down the specification, and for F2, so let me jump back somewhere where I have the specification. There it is. So if we encode now the specification in F2, so there is no way to write it down in a nice way, so at least not known to me. And then we actually end up that we have a specification for each single output bit, and that's has exponential size. So that's, yes, because the as Massimo is pointing out, the specification is natural over the integers, but not over F2 or GF2.
Other questions, comments?
There's one in the question answer.
Could you use the Chinese remainder theorem to do this modulo p for a bunch of primes p whose product is larger than the largest possible coefficient? That would also allow parallelism, suggests Victor.
So what I did not show today, but what we actually do is that we do modulo computation, but not modulo a bunch of primes, but we have, so when we have here the specification going up to 2n minus 1, that we calculate modulo 2 to the power 2n. So that when we encounter monomials with coefficient that are larger than actually the largest coefficient in the specification, then we reduce modulo that coefficient. And this helps for certain multiplier architectures. And with that, we are also actually able to verify truncated multipliers, so where we cut off the most significant output bits.
So it's an interesting question, what would happen to the verification step if you have to certify the Chinese remaindering in proof system also, I guess.
Yes.
So Alexander is asking, I'm probably missing something, but are there any lower bounds for the technique for some formalization of the approach?
I don't think that there exist really like shown lower bounds for this technique. So at least I'm not aware of these of results on that.
So I don't know which people can unmute or not. I mean, Paul Beam is a good person to comment on this.
Yes.
I think that the point, this was conjectured to be for CDCL solver, this was conjectured to be hard. I mean, it is hard in practice, and maybe there's a resolution lower bound. And then Paul Beam and Vincent Liu actually provided polynomial size resolution proofs, even in regular resolution, so a restricted form of resolution. However, the polynomials are a bit too large for this to actually fly in practice, firstly. And secondly, my understanding is that actual real-world SAT solvers stubbornly refuse to find these refutations, even when you try to give them fairly heavy hints what they should do. So since already resolution can do pretty well, it's hard to see what one could do. But one interesting question, I mean, if you're looking at essentially what, so my understanding of this is that essentially we're doing polynomial calculus over the field of rationals. And one thing you could ask that I think theoreticians have not been asking is how different reduction orders would affect things. Because when you're doing polynomial calculus lower bound, on the theory side, we usually do a degree respecting order, what Rasborov calls an admissible order, because we want degree lower bounds, and these we can then leverage to get size lower bounds. Here you have some kind of lexicographic order that actually does not respect degree. And it could be interesting to see if you could get, for instance, separation results between somehow polynomial calculus, which has to respect, say, lexicographic order or degree lex, or like questions like that might be interesting to do.
Yes. But there I think, like, as you say, I mean, if you do degree lex, then you need to pay attention that you don't lose this nice property what we have, that we simply write down the Gröbner basis by writing down the gate polynomials. Because I think if you do the degree lexicographic ordering, for example, then and I don't think then you can write down the Gröbner basis so easily, and then you would need to do some Gröbner basis computation. And I don't think that's I think that then it gets rather complicated again.
So just a comment about the relationship with CDCL and the question about whether this method does better. In principle, this method is, on simple multipliers, is something like quadratic in the bit width, roughly, because, but the best upper bounds we have for resolution are, much higher polynomial powers, n to the 5th, n to the 6th. And in practice, the solvers are, even with super hints, are a factor of n worse. So they're just not, it's not clear it's a theoretical barrier to doing better, but the difference in the polynomials, there really isn't going to be a way for CDCL solvers to match the kinds of low degree polynomials that you get out of these algebraic techniques.
So I think this comment is related to what Oded is writing in the chat. So is there an intuition that explains why multipliers are easy for the algebraic technique when they're hard for CDCL? Are there more examples where this method is better than CDCL beyond multipliers? I don't know, Paul, do you want to comment, or Daniela?
One other comment. So the resolution has good theory. I don't think there really aren't lower bounds, by the way, that are larger than just the sizes of the multipliers for solving these problems. So these algebraic methods seem to be very efficient.
I don't know if it's an answer, but one observation is that the algebraic framework allows you to write down the specification in a very nice way as this exponential sum, what we have on the slide now. It's not at all clear how to write this sort of in a clean way as a CNF formula that is obviously correct. I don't know if that's a good answer, but that's like some intuition. Maybe.
Certainly being able to use these large coefficients is something that CNF can't really do well at all.
Massimo is saying, sorry for spamming, but I got curious. Well, I guess this is not spamming. In the incremental layered approach, is it a good idea at each step to extract equations for the next computations, even if they violate the Gröner-Bayes property?
So there, I'm not sure actually what you mean with to extract equations for next computations.
I think I will just try. I think I will just try to unmute myself. Now I was saying in the layer approach, you do one layer and you get some polynomial equations, right? And then
Yes.
you do the other layer. And of course, you can use I mean, that's the point of the layer approach, I guess. You use the equation that you get from the previous layer into the next layer, right?
Yes.
But this equation may not be, they may not fit well with the idea that you want to keep a Gröner-Bayes basis. And still, they may be they may be good to keep around, right?
Yes, so what we do is in this algorithm. So we start here at the most significant bit, and then, as you said, so we reduce by one slice, and then we receive here so this remainder of one slice, which then we then use in the next smaller slice again. So we always add them up to the specification of the next smaller slice. However, the gates itself, which are in the slices, they always form a Gröner basis. Because also if we make here the cuts, we still have this property with the ordering. So we always keep the Gröner basis property.
Okay, I think I have an understanding of the process that was a little bit different, which was a different idea that you may verify maybe just like a prefix of the output, and during this verification process, you of course get a lot of some equations that relate to that part of the circuit, and then you bring this equation to the other layers, and you sort of verify prefix of the output one by one, but in the different direction actually. So I think I understood differently the process. I'm sorry.
No, I mean actually, I hope now I'm getting right. What you're saying is so you would like move the gate, like the constraints between the layers and use them early in the verification process, because this might help to cut down the size of the polynomials. And then that's actually possible, because this allows us the Gröner basis algorithm to do. So when we have our Gröner basis, and no matter what computations during preprocessing we do in our Gröner basis, we still have a Gröner basis. We are free to choose the reduction ordering. we just need to make sure that in the end that we reduced by all polynomials that were possible, but we could definitely do so and put polynomials to different slices if that's necessary and helps to keep to reduce the number of the monomials. But I have to say, I haven't seen that too much in practice, that it really would help to move gates between the slices.
I think it's getting time to wrap this up. I'll just try
Thank you.
to summarize. There's a lot of things happening in the chat, and there's one final question in the Q&A. So in the chat, we have one more comment regarding the intuition why algebra is helpful. It might be related, writes Armin, to being able to capture the carry polynomials. There's more than one bit of information going from one column to the next. And then there's a question by Oded follow-up. Is there an illustrative example that is easy for CDCL but hard for the algebraic approach? And the answer is kind of no, and maybe kind of yes. It's no in the sense that if you would allow formal variables for negative literals, also known as dual variables or twin variables, then it's not so hard to see that this algebraic reasoning we've seen now can, at a theoretical level, can simulate efficiently anything that resolution can do, but it's exponentially stronger. So if there's something that's easy for CDCL in theory, but hard for the algebra approach, it would have to be because of a kind of blow up issue, because you get monomials like where you would like to have negative literals, but you don't, and so things blow up. And as Armin is noting then in the chat, so this other equivalence checking that Daniela had is, in practice at least, easy for CDCL, but in practice doesn't seem to work with your algebraic approach. Although I guess we don't have a lower bound for that, actually. And that's another like possible question at the intersection of theory and practice, maybe, if you could quantify if this step is somehow hard, if you have to encounter a polynomial blow-up. I guess it is correct to say that just in practice it doesn't fly.
Yes.
And you can observe that the polynomial blow-up is what seems to kill it.
Yes, because I think the reason are these, as I showed, the sequences of OR gates, which led to this explosion in this algebraic approach, but they can be fairly easily dealt with in the CDCL solvers.
And then the final question in the Q&A, it was mentioned that your mention is quadratic in the bit size. Is that mostly because the specification is quadratic in size? If so, what would happen if you use the Karatsuba multiplier, which is only n to the a, where a is the logarithm base 2 of 3?
So with the quadratic in the bit size, yes, I mean we already introduced with the quadratic size of the specification, as you pointed out correctly. What would happen if you use a Karatsuba multiplier? I mean, our approach also always relies on this, on this internal cancellations, because part of the multipliers are always this full adders, which have this linear shape. So that's why the quadratic size comes actually from the specification. And I don't know if the Karatsuba multiplier is also internally built with only that. So I don't know if the specification of the Karatsuba multiplier is small, but during the verification, then because of the shape or the structure of the multiplier, this gets hard. So I actually have to say I have never tried these Karatsuba multipliers before.
So I'm not sure. I'm thinking that this is more like, or this. I should know this better, but I guess I don't. So I'll just speak. But I think these are this is the algorithm for multiplying like really large integers efficiently. So I guess you wouldn't see them. Like the name of the game here is, I guess we don't get to choose the circuit design. Like someone gives us a nifty circuit design and wants us to verify this somehow, right? And that's why we have to work with what we're given. Okay, one very, very final question from Paul Beam. What about Wallace tree? Is that the same size as the circuit? So in terms of performance for the specification, I guess, yes.
Yes, so also for Wallace trees, we did not see also there. I think we have this quadratic size. So they are definitely easy for the algebraic approach to verify, because also the Wallace trees, like they are built out of full and half adders, but only they are arranged like in a different pattern.
So I guess, so with this, I think we should wrap it up. So the problem is now that we're almost out of also the second hour, because you gave a far too interesting talk, Daniela, generating far too interesting questions, or maybe the chair was doing a poor job in moderating and cutting things off earlier. But then again, having these kind of questions and discussions is, I guess, part of what this is all about. I suggest the following, that we take a 10-minute break. And then let's just reconvene and see if there's anyone having energy for talking more, or if we should just discuss whether we should talk more at some other time. Does that sound like a plan?
It's fine for me.
So, okay, but then we're pausing now and reconvening, let's say 1925 European time. So that should be what, like 10:35 Pacific, whatever. In 10 minutes from now. See you in a bit.
See you.
For those of us who wish to reconvene. So I guess we're starting to come back from the break. And there are still some valiant souls around. What do you say? What should we do? What's on the menu? I'm not entirely sure how to do this. Like if we should just do like the second technical talk now, if people are up for this, or if the speaker is up for this, I have no idea, right? This is.
You mean, what? I mean, I didn't actually expect that it's already like 7:25 here. So I prepared kind of a shortish talk about how we do the proof logging in our tools, but I guess this also takes, I don't know, 15-20 minutes around. So I don't know if we should do that right now or if we just do.
Let's ask the first one. Would it be an option from the speaker side? Let's start with that. I think that's the most important question. Like listeners is a second concern, but if we don't have a speaker, then it will be really hard.
You mean I'm still there?
You're still there. Okay. So what do people say? So should we like take a show of hands or something? People who want to hear like a 20-ish minute talk. If you see on the participant panel, like you can raise your hand. Do you know how to raise your hand? If I click on the participant list, then at the bottom I have some choices like mute me or invite or raise my hand. And I'd like to see some. So if you're raising your hand now, then you're voting for having a talk. And there are some hands going up in the air.
Yeah. 2 from my group. There are more.
So what do we do? Okay, so if we take all our hands down, and then we take so please take your hands down, and then we take a quick vote. Just people who say, no, this is fascinating, but there's no way I can listen now. Better to reschedule some other time. People who voted before take their hands down, and now hands up for people who want us to find another solution. Blank votes are also okay. I'm just trying to. So people who want to reschedule to some other time, this is fascinating, but I just can't attend right now. Jakob, why didn't you chair this more properly? Okay, I think we have a majority for actually running the talk, so let's do a 20-ish minute or whatever. I'm a little bit hesitant about your time estimates, Daniela, regarding your first hour talk, but let's see how we do this. Let's keep going.
Yeah, no, I try. So
we are doing a talk on, I guess, verification for verifying the verification.
Yes. So that's where we are. So this was my slide. So meaning that whether we can trust the verification process. So we want to generate machine checkable proofs. And yeah, I will skip now this repetition part. So we already saved 2 slides. So we are now concerned here with a proof system which allows us to reason over algebraic polynomial equations. And there is this, like in proof complexity, well-known algebraic proof system called the polynomial calculus, which allows us to derive which allows us to write down whether a polynomial is contained in an ideal generated by a set of polynomials. So we have given here a set of polynomials G and a set of polynomial F, and then in the polynomial calculus, a proof to see whether F is contained in the ideal generated by G is a sequence of proof rules, where each proof rule is either the Boolean axiom, which says that the possible values are only 1 a 0, or by the addition and the multiplication rule. And these addition and multiplication rule actually monitor the properties of the ideal which we had previously, so that the ideal is closed under addition or by multiplication by any other polynomial. And when we take now an example, so we have here a small circuit consisting of an inverter, so B is the negation of A, and then C is the conjunction of A and B, so C is actually in fact computes A and not A, so that's why the output is always 0. So we have here our specification. C is equal to 0, and that's what we want to show, that from these two gate constraints we can derive that C is always equal to 0. And here you see the corresponding proof tree, or respectively here the proof sequence as it would be written down in the polynomial calculus. And what you see here is that now is the question whether or how easy or how we can now check this proof. And you see that's not easy doable, because like seeing this polynomial, it's hard for us to decide how this polynomial was actually derived, so whether it was the addition rule or the multiplication rule that was used. So the polynomial calculus is actually quite hard to check. So that's why we introduced a different, a more concrete proof format. So we translated the polynomial calculus into the practical algebraic calculus, as we call it, where the given gate and Boolean value polynomials serve as axioms. And then we have instances of the addition and multiplication rule to derive the polynomials. Yes, so that's the syntax. I will jump over that because it's anyway way easier to see here on our previous example. So we have here the given polynomials, and then we have here now the sequence of the multiplication and the addition rules. And you see that here for the multiplication rule, for example, we first write down the operator and then the two polynomials which were used in the multiplication step to derive the conclusion. And for proof checking, we then simply traverse over each proof rule. And for each proof rule, we check whether we know already the indices, so the antecedents. So for multiplication, we only need to check this for the first polynomial. And in this case, we see the polynomial. Yes, we know it because it's one of the given polynomials. And the second property we need to check for each proof rule is that the conclusion is actually correct. So in this case, we multiply these two together and then get then the conclusion polynomial. And that's what we do for proof checking. And you see with this new format, it's actually rather easy to do so. So as I said, all of our proof rule contains 4 components: the operator, the 2 antecedents, and then the conclusion, where the operator is either a plus or multiplication. And then we check the connection property, namely that we already know the antecedents. For addition, we need to check this for both antecedents, for multiplication only for the first one, because that's how the ideal is defined. And then we check the inference property, namely the correctness of each proof rule, so that really the conclusion is can be derived from the antecedents using the given operator. And furthermore, we also make a target check, so that at least one of the conclusion polynomials in the proof is equal to the target which we want to have, for example, the specification of the multiplier circuit. Yeah, and that's the pseudocode for the proof checking algorithm, which I just explained, but I also will jump over that. And then I'll briefly want to mention how we generate these proofs in our tool. So the given multiplier, the given polynomials are obviously all the gate polynomials and the Boolean value constraints, which we derive during modeling. So we simply print them down while modeling, and this will then act as our initial constraint set of the proof. And then for the actual proof generation, we need to distinguish whether we are in the pre-processing, so in the variable elimination step, or in the spec reduction step. Yeah, in the pre-processing step, as said, we have the given Gröbner basis. We want to derive a simplified Gröbner basis by always taking two polynomials from the Gröbner basis, then do this reduction step. The remainder will then be added to the Gröbner basis, and both previous elements from the Gröbner basis will be thrown out. So that's the reduction step we do here in the pre-processing. And in the spec reduction, we have our ordered Gröbner basis, we have our specification, and yeah, now we want to determine whether the specification is containing the ideal generated by the Gröbner basis. Initially, we set our remainder to the specification, and then we always do this reduction steps until like we traversed once through the complete Gröbner basis and check whether the result is 0. So also here we always do the same reduction steps as here in the pre-processing. The difference here is that in pre-processing, both polynomials of the reduction steps, so both here the P and Q, are already contained in the Gröbner basis, so they are elements from there. While in the spec reduction, the specification, so the polynomial which is reduced by the Gröbner basis, is not known to us because we want to show it that it's contained in the ideal. So only here the second element is contained in the Gröbner basis, and that's what we need to keep in mind when we write down the proof rules. But first to the actual reduction step, when we have P and Q and we want to get the remainder of reducing P by Q, then we do the following steps. So at first we calculate the quotient of dividing P by the leading term of Q. Then we do a multiplication step and an addition step. And I better show this quickly on an example because then it's easier to see what is going on in this algorithm. And for that, I take again the pre-processing example, which I showed before the talk, where we have our ideal and we reduce the first polynomial here by the second polynomial in order to eliminate the y. So the first polynomial acts now as the P in the reduction step, the second is the Q in the reduction algorithm. And at first, we calculate, so we divide P by, so this is the first polynomial by y and write down the quotient. So we see here the only monomials are containing y's here plus xy and here minus y. We remove the y, so get here x minus 1. We multiply this quotient now by our polynomial q to get here this result and add it to p to get the final result. And this polynomial will then be added to the Gröbner basis and the other two will be removed. And when you compare it to the previous slide, you see that that exactly is the elimination ideal as we had it previously. Yeah. So that's where we want to write down now the proof steps. And here are the only polynomial operations that are done like with our given set of Gröbner bases. So that's where we need to write down the proof steps. So since we have a multiplication and an addition operation, we print here a multiply rule and an addition rule. And as I said, for the pre-processing step, this is really fine, because both polynomials p and q are contained in the Grödner basis. So proof checking is fine here. But in the specification reduction, the first polynomial is not contained in the ideal. So that's where we run into trouble here now in the addition rule, because if you would print it down like that, the proof checking algorithm would say us, hey, this polynomial p, which is the specification, is not known to me. That's an error there. So instead, what we do is we kind of have printing flags. So if we're in the pre-processing step, then we print this addition rule. Otherwise, we collect the factors on, so that the results here of multiplying the quotient times the g on the stack. We keep the stack, and when we are done with the specification reduction, then at the end we print 8 rules for this stack. So let me go a little bit into detail here why this works.
Daniela, so there's a question also. I don't know if you want to take it now or later, but Paul asks, in the DAG version, isn't this just always substitution? Do you have simpler code for that case? This reduction when the leading terms are always this output gate of the circuit, I think.
No, I mean, actually we always do here this division by the leading term, multiplication, and addition step. So what would you mean with simpler code? I mean, actually, what this boils down to is that we always substitute the tail of Q into all occurrences of the leading term for Q. But so far, so that's really these steps as we execute them, and also that's how we write down the proof logging steps. Always this multiplication and the addition rule. I hope this answers your question.
Okay, thanks.
Good. Yeah, so that's where we were. So because what happens in this spec reduction is that, like in the first step, this R is equal to the specification F, and then we always kind of plug in here the steps which we did in the reduction algorithm until we get here our final remainder, the Rn plus 1, which is equal to 0. And along that, we always kept here these results of the multiplication steps on a stack. And when we now unfold here this reduction, we actually see that we can write down this Rm plus 1 as F plus the sum of all these elements on the stack, or in other words, that F is equal to -1 times all the elements on the stacks. And that's exactly kind of what we then write down here with a sequence of addition rules and do one negation step to reach the final specification. So that's how we write down the proofs in the amulet. Yeah, and then quickly, finally, we worked a bit on the proof format. So this was our initial format, where we really wrote down a multiplication and an addition rule, also for all the Boolean axioms. And we recently modified this proof format to allow us more as a shorter and more concise proof. So the first step is that we handle now the Boolean variables implicitly. So we remove them from the given set of polynomials, and also now in the proof rules, we always calculate again that a times a, for example, here is equal to a instead of a squared. So that's where we hide these rules. The second optimization is, because you see here that we write down here this conclusion polynomials minus a times b, again here is an antecedent. So we write down polynomials multiple times. So instead we now introduce indices. So we label also all the given polynomials and then introduce a label for each proof rules, because this allows us then to address the antecedents in the proof rules to reduce the size of each rule. And the third thing which we did is that we added a deletion rule, because after checking each proof rule, the conclusion polynomial would then be added to the constraint set. So with each proof rule, our constraint set grows and grows and grows. But sometimes it happens that you don't need a proof rule anymore in the future, and maybe during proof checking you already know this. So you can write down a deletion rule to remove it from the constraint set, to keep the size of the constraint set small. And this all helps to reduce the size and the memory usage of our proof checker. And yes, that's where I will stop right now. So that's what I wanted to talk about proof checking and proof logging for our application.
So a question is, having labels or line numbers for the constraints, is that mainly to bring the proof size down? And if so, like, how important is it?
Yes, so it brings the proof size down, because we now write down conclusion polynomials only once. And this, together with hiding kind of this Boolean value constraints in the proof, gave us kind of an order of magnitude shorter proof. And this also reduced the proof checking time, because quite a lot of the proof checking time actually comes from parsing the proofs. Yes, and as Massimo is pointing out, you don't need to look for a polynomial in the database. You access the database with the corresponding index, and then you see whether the proof rule is then correct.
Yeah, I guess, though, I mean, if you wanted, I guess you could do some hashing or something there. So it's not clear to me that that's like the killer. Is it? I would have guessed that it's more about proof size, but I don't know if that guess is correct.
Yes, I mean, so that's what we did in our older proof format. So there we did the hashing. So in our older proof format, so there when we explicitly have written down the polynomials, there you could only introduce a polynomial once. But now with these indices, we still have the effect that now you can introduce or add a polynomial to the constraints set multiple times using different indices. So now we have kind of the notation from like sets to multisets.
I'm also a little bit curious about this deletion. Oh, sorry, I interrupted you.
No?
So I think when you're doing for CDCL solvers, then deletion is important for proof verification performance, because you're going to do a lot of reverse unit propagation, and that of course can scale linearly in the size of the database. So bringing the database size down is important. But here I think you're only doing like explicit derivations. So it's still like memory usage still becomes an issue.
Not time-wise, but space-wise. There, yes. So especially for this really large multipliers, which we had with this 2048, I was like able to bring our cluster to its limits when we don't do the deletion rule.
Oh, wow. So that's related to, I think, a question by Paul that is appearing in the chat. How large do the working sets in the constraints you deal with get?
So we don't have a number right now, but it's more than millions. So for this large benchmarks, it's more than millions, because you see already the one I showed you, you have more than 2 million. So for this 512 bit multiplier, you have more than 2 million nodes. So for each of the nodes, you already write down one gate constraints. And yeah.
So where do we go from here? What are challenges that you currently cannot do, or or the problem is solved now? We should move on and do something other than circuit verification because we know how to do this.
I mean, that would be nice. So no, but we are at this point right now that we can verify this especially for the multipliers, that we can verify the different architectures as they are right now. So like that you really design, okay, I want to make this architecture like the Wallace tree and the carry look ahead adder. So I think that's there we are pretty safe right now. But in practice, then the hardware developer, they use some synthesis and optimizations to reduce again the number of the gates, and also then to optimize the circuits. And these optimization techniques, they kind of destroy the still somewhat regular architecture of these multipliers. And so that's where kind of the challenge is right now, because these the destruction of the architecture leads to that the polynomials grow again, because we don't have these nice patterns, that we have these internal cancellations. And that's where yeah, we're kind of stuck right now, where we are still work needs to be done.
And these techniques you had for slicing and dicing the circuits and eliminating those somehow don't work as well for these optimized designs?
Yeah, because somehow this techniques, they also rely on the boundary, so that for example, we have this nice clear cut between the final stage adder and the accumulation step to do this adder substitution. And when the gates are optimized, these clear boundaries do not exist anymore. So for example, then my tool does not know where this clear cut needs to be done, or whether it, or actually it's even unclear if it still exists. So that's where I think we need to think further on how to handle these architectures. So
would you verify these architectures directly, or is it conceivable that you could do things like equivalence verification? Like you start with a stupid circuit before optimization and you know that it's correct, and then I provide proof step by step that yes, this optimization step did not change the functionality of the circuit.
yes, I mean that's also kind of what is done in practice. So where you start with this regular multiplier or with this regular circuit, and then step by step verify the correctness of the optimization. But I mean in practice this needs to be done manually, and I think that's also kind of what we can do, is that we verify the equivalence of these multipliers. So like, as you said, this stepwise, so that we do not directly jump into this really complicated, super optimized, but verify each optimization step. This could be a possibility.
So any other questions? So one observation that might be worth making is that on the in the theory side, you can discuss how to measure proof size for polynomial calculus proofs. And in fact, you get very different proof systems depending on how you represent the polynomials. You can represent the polynomials as linear combinations of monomials, and that's like classic polynomial calculus. Or you can say, well, I would prefer to write down my polynomials in more efficient ways, some kind of binary decision diagrams, or maybe as general circuits. And then it becomes much harder to prove lower bounds. So then actually pretty soon we get into settings where we cannot prove any non-trivial lower bounds. But then an observation is that here, for what you're doing here, this seemingly naive model where a polynomial is a linear combination of monomials is in fact, like that is what a polynomial is for you. Is that true?
Yes.
So that lower bounds in this setting that theoreticians would come up with are potentially like relevant in that sense, in that they correspond to a computational model that would exist there out in the real world. Or are you like representing your polynomials in smarter ways?
I mean, we really represent them as sequences of monomials. So we do not have like internal like this decision diagrams or something like that. So we really have it as sequences of monomials, and yeah, for the terms we use a hash table. So we share the terms internally. But for representing the polynomials, they are really just a sequence of monomials.
More questions, comments? Before we say that Daniela has worked hard enough for us.
Yes, sorry for taking so long.
I think we all enjoyed it.
I hope so.
Otherwise, we wouldn't have stuck around. Okay, so I think so that maybe we're calling it a day. Thank you so much again, Daniela, for this talk. And then I'm thinking about for next week, I think we're having a deep dive into pseudo Boolean solving. So don't miss that, 5:30 European time next Tuesday. Okay, thank you so much. That's it for today.